Bismillahirrahmanirrahim. Assalamu alaikum, students. Today, we are going to discuss another idea. The idea is about the specification of a state. Let me write the specification of the state I should write state of a system, state of a system. But in the light of quantum mechanics. This is our today's topic. We will illustrate the topic through certain examples. I hope that will help you in understanding the content of the lecture. So what is the idea of specification of the state of a system using quantum mechanics or in the light of quantum mechanics? Let me give you an example first. First, you need to know that we specify state of a system in many ways. For example, in classical mechanics, we use the idea of phase space, where the state of a system of f degrees of freedom is specified by f generalized coordinates and f corresponding generalized momenta. That is a way of specifying state also. But in quantum mechanics, the things are different. We have different notion of specifying the state of the system. I want to clear that so that we can move forward in our course. Let me call it example 1. In example 1, what we do, we consider a system consisting of a single particle considered fixed. We consider that particle is fixed, considered fixed in position, fixed in position. Let me write it clearly. Fixed in position, but having a spin half. This is our first example. So I have a system which comprises of a single particle. That particle is considered fixed in position. That means it is localized, but it has a spin half. That means its intrinsic spin angular momentum is half h bar, where h bar is h by 2 pi. and h is Planck's constant with value 6.6 into 10 raised power minus 34 joules second, right? So if I have such a system in which I have a single particle which is considered fixed in position, but it has spin half. So if it has spin half, its intrinsic spin angular momentum is half h bar, where h bar is h by 2 pi. H is the Planck's constant, which has the value which I have specified. Now, in quantum mechanical description, the state of this particle is specified. How we specify its state? We specify in quantum mechanical description the state of this particle by the projection M. Let me write here. By the projection M of its spin along some fixed axis, which we normally choose to call the z-axis. Now, this quantum number M, which is basically specifying the projection of its spin along some fixed axis, which we call z-axis, this quantum number M can assume two values. This quantum number can be plus half, or it can be minus half, right? And we roughly say that the spin can point either up or down with respect to the z-axis. So it is this quantum number, the value of this quantum number M, which specifies the state of this particle. So this particle can exist only in two states. If it is fixed, it has to be half. Quantum mechanically, it can exist only in two states. One state is specified by the value of M being half, and another state is specified the value of this quantum number equal to minus half, which in other words, we say that it can point up or down with respect to the fixed axis, which we call z-axis. So you see here, it is the idea of the quantum number which we use in specification of the system in question. The values of the quantum numbers which are concerned with the system specify the state of the system. So in this situation, we have two states. One is specified by the quantum number M being half, and the other state is specified by the value of M being equal to minus half. Let us take another example. I call that example 2. In example 2, consider a system consisting of n particles considered fixed in position, fixed in position, but each having but each having spin half. Now, if my system is like this, I have now system consisting of n particles which are assumed fixed in position, but each have a spin of half. Now C is this extended system of example 1. In example 1, we had a same system, but the particle number was 1. Now I am saying if my particle number is n, but all particles are having spin half and they are fixed in position. And this n can be large in general. It can be of the order of Avogadro's number 6.023 into 10 raised power 23. Now the quantum number m of each particle can then assume two values, half or minus half. So for each particle, m can be plus half or minus half. That means, as we already discussed, that with respect to some specified axis called the z-axis, it is spin can be along that axis or anti-parallel to that axis, which we label as up or down state. So for each particle, there are two states possible specified by the value of m. It can be half or minus half. But when we talk of the state of the entire system, which is comprised of n such particles, then the state of the entire system will be specified by the values of the corresponding these magnetic quantum numbers. We call sometimes this m as magnetic quantum number. So there will be m quantum numbers, m1, n quantum numbers, m1, m2, up to mn. Now, let me correct this pen. Okay. Mn, which specify the orientation of the spin of each particle. So m1 is the magnetic quantum number pertaining to particle 1. M2 is the magnetic quantum number pertaining to particle 2. And similarly up to Mn, there are n particles in the system. So the set of these n quantum numbers will specify the state of the entire system. Each m can have two values, half or minus half. So to specify the state of the entire system, we have to list or specify all the values of these n quantum numbers, right? This is how we use the idea of specification of a state using the quantum numbers. Let us take another example. I call that example 3. Consider a system consisting of a one-dimensional simple harmonic oscillator whose position coordinate is x So if I have such a system, I have a system which consists of a one-dimensional simple harmonic oscillator whose position coordinate is x. You know the definition of the simple harmonic oscillator. It is that oscillator which oscillates under the action of a force. F of x is minus kx, where x is the displacement of the particle from the mean position. K is the constant of proportionality. So if I have such a one-dimensional harmonic oscillator, in quantum mechanics, how we specify the quantum states of this one-dimensional simple harmonic oscillator? Remember, in quantum mechanics, this simple harmonic oscillator, this one-dimensional simple harmonic oscillator can exist in the states which have energies given by En is equal to n plus half h bar omega, where omega is the classical angular frequency of oscillation. The classical angular frequency of oscillation. Now this quantum number n can assume values n equal to 0, 1, 2, 3, and so on. So if n is equal to 0, the energy of the oscillator in that ground state is half h bar omega. It can exist in another state characterized by n equal to 1, in which the energy of the state is 1 plus half, that is 3 over 2 h bar omega, and so on. So this principle, this quantum number n, which we let us call it n, this quantum number n here specifies the possible quantum states of this oscillator, right? So it can exist in the states specified by the value of n. So in this example, you see also there is a quantum number which specifies the state of our system. So let us take another example. We call that example 4. Consider a system consisting of n simple harmonic oscillators. So if my system consists of n simple harmonic oscillators, which I assume as weakly interacting and one-dimensional. So if I have a system consisting of n simple harmonic oscillators which are weakly interacting and are oscillating in one dimension, then the quantum state of this system can be specified by the set of numbers n1, n2 up to nn, where the quantum number ni refers to the ith oscillator and that can assume the values 0, 1, 2, 3, and so on. So when you have a system consisting of n simple harmonic oscillators which are weakly interacting and are oscillating in one dimension, then you have to specify the state. In order to specify the state of the system, you have to specify all the n's, where each n can have values 0, 1, 2, 3, and so on. Right? Let me take another example. I will change the color. I call it example 5. In this, what we do, we consider a system consisting of a single particle. We assume this particle has no spin, without spin, confined within a rectangular box, within a rectangular box, so that the particles coordinate. Let me correct my pen. So that the particles coordinates lie within the range 0 less than or equal to x less than or equal to lx, comma 0 is less than or equal to y, is less than or equal to ly, and 0 is less than or equal to z, less than or equal to lz, but otherwise subject to no forces, subject to no force. If this is my system, let me change the color of it. So if I have this system, a system consisting of a single particle which has no spin, is without spin, we are disregarding it as spin, if it has any, confined within a rectangular box. It is in a rectangular box. So particles coordinates lie within the range, its x coordinate can be equal to 0 or greater than 0, but maximum it can be Lx, and y coordinate has the restriction and z coordinate has the restriction. So it is understandable that Lx, Ly, Lz represent here the sides of the box or edge lengths of the box. We assume this is otherwise subject to no forces. So our particle is in a box, it is restricted to stay in the box, and that restriction is specified by the restriction on its x, y, and z coordinates. But inside the box, it is free. There are no forces acting on it. Now, how we specify quantum mechanically the states of such a particle? Remember, the wave function psi of the particle, which has some mass m, must satisfy the Schrodinger equation. This is a famous example, particle in a box. You must have gone through it, but I have to highlight one thing here. So the wave function psi of the particle under consideration of mass m must satisfy the Schrodinger equation given by minus h bar square by 2m dou 2 over dou x2 plus dou 2 dou y2 plus dou 2 dou z2 psi equal to E psi. I name it first. So this is the quantum mechanical description of this particle. So its wave function, if it has mass m, we're taking m as the mass, must satisfy this Schrodinger equation. H bar is h over 2 pi, h is the Planck's constant, dou 2 x by dou 2 of dou 2 by dou x2 plus dou, these are second order partial derivatives. So it must satisfy this equation. And to guarantee confinement of the particle within the box, because we are specifying restrictions on the particle that it is confined within the box, and to guarantee that confinement within the box, this psi must vanish at the walls. That means at the walls, this psi must be 0. Now the wave function having these properties has the form. I will use another color. The wave function which has the properties that psi vanishes at the walls, they get that guarantee the confinement restriction on the particle. That wave function has this form. Let me write psi is equal sine of pi nx x over Lx, sine of pi n sub y over Ly. And there is a third factor, sine of pi nz z over Lz. Let me name it second. So this is the form of the concerned wave function for this particle. Sine pi n sub x, x over Lx, sine pi ny, y over Ly, sine pi nz, z over Lz. Now this equation 2 satisfies the Schrodinger equation, equation 1, provided that the energy of the particle is related to these quantum numbers nx, ny, and z through the relation. Let me write that. The relation is E is equal to h bar square over 2m pi square times nx square over Lx square plus ny square over Ly square plus nz square over Lz square. Let me name it equation 3. H cross square by 2m pi square nx square over Lx square plus ny square over Ly square plus nz square plus Lz square. So first we said that the quantum mechanical description of this particle is this given by this scenario, which we discussed, that its wave function must satisfy this Schrodinger equation given by equation 1. Then we said to guarantee the confinement of the particle within the box, psi must vanish at the walls, and the wave function which has this property is given by 2. Then we said that this equation 2, that the wave function satisfies Schrodinger equation 1, provided that the energy E of the particle is related to nx, ny, and z through equation 3. Also, you know that psi is equal to 0 properly when x is equal to 0 or x is equal to Lx. They are the boundaries along x direction. Psi is equal to 0 when y is equal to 0 or y is equal to Ly. It is equal to 0 when z is equal to 0 or z is equal to Lz. Provided when that happens when the three numbers nx, ny, and z assume any discrete integral values. Nx, ny, and z assume any discrete integral values. Now the state of the particle under consideration is then specified by stating the values of assumed by these three quantum numbers, nx, ny, and nz. So the state of the particle in question here will be specified by stating the values of these quantum numbers, which can assume any discrete integral values, while equation 3 will give us the corresponding value of the quantized energy in that particular state. So once you specify the state by specifying the values of nx, ny, and z, which can assume any discrete values, you are specifying the state of the particle, then you can, using equation 3, find the energy of the particle in that particular state. So I hope the things are clear how in quantum description, the state is specified by the quantum numbers concerned in the problem. So before leaving, let me summarize the lecture. So our lecture was about the specification of the state of a system in the light of quantum mechanics. First, we considered a simple system, a single particle considered fixed in position, which has spin half, so it can exist in two states. Those states are specified by the value of m. Then we considered the similar system, but the particle number was n. Here you have to specify all n values of the m's to specify the state. Then we considered a simple one-dimensional harmonic oscillator, and we said that it is the value of n which specifies the quantum state of the particle. Then we considered n particle system consisting of simple harmonic oscillators which are weakly interacting and one-dimensional. Here also there will be a set of quantum numbers, n quantum numbers, and each n can assume value 0, 1, 2, 3. So you need to specify all n quantum numbers to specify the state of the system. And say as then we consider this particle in a three-dimensional box, which inside the box is assumed to be free. Then here we have three quantum numbers, nx, ny, and z. The specification of these three quantum numbers specifies the state of the system. Incidentally, you need to here understand that when you say the system consists of n particles in this situation, each particle having spin half, it is assumed that we are taking the system of n particles as weakly interacting with each other. Then you need to specify individually all the m's to specify the state of the system. So I hope the idea is clear to you. In quantum description, the state of the system in question is specified by the set of quantum numbers concerned in the problem. Sometimes it can be a single quantum number, sometimes it can be a set of quantum numbers, depending on the situation. So quantum numbers specify the state quantum mechanically. That's all for today. Thank you. God bless you. Don't forget to like, share, and subscribe my channel. If you have queries, you can comment in the comment box. I will try to answer your queries, inshallah. Thank you. God bless you.